Hello, this is Professor Matt Katroulis of Rio Hondo College with the final organic chemistry section for the Chemistry 110 course with experiment 17, which is focused on carboxylic acids and esters. So in part A, we focus specifically on the acidity of carboxylic acids. Among the functional groups in organic chemistry, carboxylic acids are by far the most acidic. Even so, they are only weak acids. And recall that weak means weak electrolyte. It means they only dissociate slightly in water. So for every 200 molecules, for example, maybe only 1 or 2 will dissociate. So here is the general reaction that we see for a carboxylic acid in water. So I've used red here to color code the acid and blue to color code water. And in a typical acid-base reaction here, water is going to act like the base. It will take the proton away from the carboxylic acid and it forms a hydronium ion. And then that leaves us with the carboxylate ion. Now you'll notice here that we have equilibrium arrows, and the arrow is mostly pointing towards the left, which means this reaction is mostly disfavored in the direction that it's written. In other words, it will mostly go to the left. If an acid is added to a salt, it primarily restores the carboxylic acid. Carboxylic acids, however, do react with strong bases, and sodium hydroxide and potassium hydroxide will be our main focus here, and those will form carboxylate salts. So here is again at the same generic acid molecule. We're adding the strong base sodium hydroxide. The hydroxide takes the proton away from the carboxylic acid to form water, and that leaves you with a carboxylate ion here and a sodium ion. Now, since these are opposite charged, we would expect them to be attracted to one another. Note that this does not mean that they are necessarily going to precipitate. It just means that you're going to have a positive ion, a cation, with a negative ion. And this whole species here would be called a carboxylate salt, or we might call it the sodium salt of the acid. Carboxylic acids that have a very small number of carbons, typically less than 5 or 6, are generally soluble in water. Why would that be the case? Again, we find that things that are polar tend to want to dissolve in solvents that are polar, like water. Carboxylic acids are not only polar, they are able to form hydrogen bonds with water molecules, and so therefore it only makes sense that they should dissolve in water. However, when there's a large number of carbons, that increases the percentage of the molecule which is nonpolar, and eventually that gets to a tipping point, and despite the polarity of the carboxylic acid, the molecule overall is too nonpolar to dissolve in water. So for the small ones, definitely will dissolve very well in water. Now the salts tend to be extremely soluble in water, even when they have a fairly large number of carbon atoms. Recall that many ionic compounds are soluble in water. There are certainly exceptions to that, especially ionic compounds where there's a 2+ charged cation and a 2- anion. But for most of these carboxylic acid salts, they will be soluble in water. Now the carboxylate salts can act as bases, and if they are added to a strong acid like hydrochloric acid, it will reform the carboxylic acid. So, for example, this was the product that we saw in the last slide when we took a carboxylic acid and added sodium hydroxide. That was a weak acid plus a strong base. Here we are adding hydrochloric acid, which is a strong acid. And since it's a strong acid, it will add the hydrogen right back onto the carboxylate ion and restore the carboxylic acid. That leaves us with the sodium ion and the chloride ion left over, and since we're in water, this will remain dissolved. Sodium chloride is soluble in water. I begin by adding acetic acid dropwise to the water in the test tube on the left. After adding several drops, we shake it up and take a closer look. And you notice that there aren't any separate layers. It might have looked like there were bubbles on the bottom, but those were just a trick of the glass. So acetic acid is totally soluble. That white solid there is benzoic acid. I'm going to go ahead and add that small amount to the water in the test tube on the right. And then I'm going to go ahead and swirl that up. So far we don't see any of it dissolving. Continue to swirl. Recall, benzoic acid has 6 carbon atoms in it. So with benzoic acid, we're just getting to the limit of solubility, and so it doesn't appear that any actually dissolves. Here I am testing the pH of the acetic acid in water. You want to look at the section of the paper which is indicated with the arrow and compare that to the pH paper to find out the pH. And then there is the pH test for benzoic acid in water. Again, you'll want to compare that top wet part to the pH paper. Pause the video if necessary. I then go ahead and take the benzoic acid in water and I put it in a hot water bath for several minutes. Now we're only going to look at the test tube on the right. It's the benzoic acid in the water. After heating, you'll notice that you don't see any crystals. With many compounds, we notice that they are more soluble in hot solution rather than cold. I have allowed the benzoic acid solution to cool, and you'll notice if we take a good look at it that the crystals have in fact come back. The acetic acid has remained soluble throughout, and there are some of the crystals if you look carefully now that the solution is cool. You see the red litmus paper. I'm going to add enough base to those solutions until I can test them and the red litmus paper turns blue. So here you're seeing the solutions after I have added enough sodium hydroxide to each test tubes to turn the paper blue. And you'll see that the crystals are gone in the benzoic acid. In effect, I have made the salt. Now I'm going to add enough hydrochloric acid to each test tube to make each of the test tubes acidic again. And we'll do that by testing and seeing that the blue litmus paper turns red. You're not seeing me actually dip the stirring rod into the test tubes to test that, but in fact I am. While you're not seeing it, putting stirring rods in to test. The red color indicates that the solution is now back to being acidic. So throughout all of this, nothing has visually changed in the acetic acid test tube. However, if you look carefully, the benzoic acid crystals are back. The carboxylate ion is now back to being benzoic acid. That ends part A. Part B of this experiment focuses on esters, specifically on their preparation and some of their physical properties, as well as their naming. One of the common ways that we form esters is through a reaction called Fischer esterification, and that is accomplished by reacting carboxylic acids with alcohols. We also need a strong acid catalyst for this reaction to go with any reasonable speed, and we usually use sulfuric acid. In the lecture, we talk about using sulfuric acid specifically as a catalyst for this reaction. However, in the lab, we normally use phosphoric acid with students, H3PO4. It is quite a bit safer to deal with, although it still has its risks. So this is the generic reaction that we would be using to combine carboxylic acids and alcohols. Notice how I've chosen to write the carboxylic acid with the OH group pointed off to the right. I've chosen to draw the alcohol with the oxygen bonded explicitly to its alkyl group and the hydrogen sticking out. And the reason I choose to do it that way is because it makes it easier, I find, for students to figure out what the product is going to be if you always write esterifications this way. So we know that water has to be produced in this reaction, so we can easily identify the water molecule right there. So we've got an OH right here and a hydrogen right there. And so we lose that group, and then the remaining group here, that's called an alkoxy group, the OR, attaches right at the carbon, and that gives us our ester. So let's do an example here. Let's say that you're asked to write a balanced equation for Fischer esterification between the reagents propanoic acid and benzyl alcohol. And we would like you to name the ester which is produced. So let's start off first by writing down the compounds. So first we're using propanoic acid, sometimes called propionic acid, that's the common name, and benzyl alcohol. You shouldn't have a problem writing the acid. The acid is the acid with 3 carbons, so propane, so 3 carbons. 1, 2, 3. And then carbon number 1 is always where the functional group is located in an acid. Benzyl alcohol might not be familiar. You might initially think that it's a benzene ring with an alcohol on it, but that would be phenol. So benzyl alcohol has an additional carbon in there, and this is its structure. You need to know this structure for the lab, so you'll probably want to write down this formula at some location. So it's simply like toluene. Remember toluene, which has a benzene ring and then a CH3, a methyl group, but instead of being a methyl group, it's a CH2 with an alcohol. You'll notice that I have drawn the molecules so that we have the OH group of the acid drawn pointing to the right, and the alcohol I have the OH drawn to the left. I could have left the oxygen with the carbon, but I chose to keep it with hydrogen here. The important thing to remember is that you're going to lose water. So we're going to lose this OH and this hydrogen. We're going to need our acid catalyst, and we'll be using phosphoric acid in this experiment. And so the ester is what you get when you simply attach this oxygen to this carbon and then get rid of these atoms down here as part of the water. So we combine those to make water. The actual reaction process itself is considerably more complicated, but this is going to simplify it. And so this is our product. You'll notice I've color-coded everything to show where the atoms are coming from. And we also need water. Let's name this compound. This group here might not be familiar, but if we go over here and we look at this name, it's a common name. It's benzyl alcohol, so it makes sense that this must be a benzyl group. That's what we call this, a benzyl group. And for the portion that comes from the acid, we just go look at the name and replace ic acid with ate, so propanoate. So the name of this compound will be benzyl propanoate. Some guidelines for carrying out this experiment and filling in the report. First of all, don't forget to answer question number 1 on the top of page 196. It's a small little space, and many students inadvertently miss it. They think it's a instruction or just a heading on the page, but you do need to answer that question, so make a note. In this video, I'm only going to show one of the 5 possible reactions. Normally, when we're doing this in class, we have one group of students perform one of the reactions and other groups perform other ones, and then everybody pools their data at the end. I'm only going to show you the second reaction, and honestly that's because they all look visually the same. So what you're going to see here is that second one. And even though I'm only doing the second reaction, you still need to complete the whole table that you see on page 196. In the column on the right, it asks for the structure and the name of the esters. So please do that. I strongly recommend that you do this whole thing in pencil as neatly as possible, because if I can't see the atoms, it makes it extremely difficult for me to grade, and I will usually err on the side of marking it wrong if I can't figure out what you did. So make sure it's nice and clear. Another major part of this experiment is looking at the smells that the esters give off, which are generally quite pleasant. Obviously, we can't do that here through a YouTube video, so you can easily look up the smells of the esters once you know their names. You can either do that by Googling the names, or you can go to the Wikipedia article on esters, and there's a large table there with many, many esters and the different types of smells that they make. And then you want to name the esters using the same logic that I used in the previous example. Be particularly careful for the one that uses benzyl alcohol, because when we have benzyl, remember that was the first name. The same thing later on when you use, for example, 1-octanol as one of the reagents. That would give you an octyl ester. Pentane would give you a pentyl. The first compound might also be tricky on that list. The second, it was salicylic acid. So the second part of the name for the first compound is salicylate. So it will be something salicylate. Let's go ahead and take a look at a video of this reaction being performed. Let's look at some models. Here's the model for acetic acid. You will notice that the carbonyl carbon is trigonal planar in shape with bond angles of approximately 120. Here is the alcohol methanol, also known as methyl alcohol, that's its common name. The oxygen has a bent structure. Let's look at both of those molecules side by side prior to reacting. You'll notice that this oxygen and that hydrogen are lost in this reaction to form water. That oxygen bonds with this carbon to form the ester. And this is the ester that would be produced by the reaction between the previous two compounds, methyl acetate. I begin the experiment with 3 milliliters of 1-pentanol, also called pentyl alcohol. And to that, I'm going to add 2 milliliters of acetic acid. Next, I add 15 drops of phosphoric acid. After thorough mixing, I put the mixture in a hot water bath. After 15 minutes, I allow the mixture to cool. Once it's cooled, I can tell that there is a very distinct odor given off by this ester. It is the pleasant smell of banana. The last part of this experiment involves the process of saponification. This is the process that we use for making soaps. And in fact, if instead of using the ester methyl salicylate, which I'm going to use today, I used a vegetable oil or lard, which is commonly used, I could actually make soap through that process. This reaction is basically the opposite of Fischer esterification. And what we do is we take ester and water, and we convert it first into a carboxylic acid and an alcohol. Now, I will not actually write the water in the chemical equation, but water is added indirectly through the use of a strong base, namely sodium hydroxide or potassium hydroxide. So that is the first major difference here, is that we are using a strong base instead of a strong acid in this reaction. And then the other problem is that the carboxylic acid, once it's formed, cannot exist in that form in strong base solution. As we already saw in part A, carboxylic acids will immediately react with a strong base and form instead the carboxylate salt. So if that doesn't sound familiar, please go back and take a look at part A where I covered that reaction. So this is the overall process. We are taking an ester, we are combining it with sodium hydroxide, although we could use potassium hydroxide. I'm not writing it out as a catalyst, it's an actual reactant here. And what we will see happen is that the hydroxyl group technically adds here at the carbon, but that would be a little bit more complicated than I want you to see. So let's go ahead and just leave it the way it's written here, which is to show that the R group here goes with the hydroxyl, and the sodium goes where the R group was. It's just going to be a switch between those two, a substitution. And so this gives us our sodium salt. So the ester becomes a sodium salt with the alkyl group being lost as an alcohol. Let's take a look at this process. So let's say we want to do the saponification of propyl benzoate. That means that at the end of the process we will end up with propyl alcohol that's called propanol, 1-propanol, and benzoic acid. So that's how you figure that out. You look at this and say, this will give you propyl alcohol, benzoic acid, and then translate propyl alcohol to the proper name of 1-propanol. And then I want to show the balanced equation for converting the product here back to the acid using hydrochloric acid. This is all going to be what you will be doing in this experiment. So I'm showing here propyl benzoate. So here's our propyl group. And benzoate means it comes from benzoic acid. I'm adding sodium hydroxide to this. So imagine, if you will, we're just going to switch this group right here and the sodium, which is technically a sodium ion, a positively charged ion, a cation. And now the alcohol is with this group right here. I have reordered these, so this carbon, the CH3, is technically this carbon, and this carbon here, the CH2, is this carbon right there. Now, should this be soluble in water? Think about this for a second. It's got 7 carbons, so normally that would be a little bit unlikely if this were a carboxylic acid, and we already saw the benzoic acid was not soluble in water. However, this is a salt, and remember, salts are much, much more likely to be soluble than the acid itself. So this is very likely to be soluble. If I go ahead and I take that compound and then add the strong acid hydrochloric acid, that converts it back to benzoic acid. Recall in part A we saw that benzoic acid was insoluble in water, so we would suddenly expect to see a precipitate formed. We also here have sodium chloride, which in water we know to be soluble. Let's take a look at the video of this process. We start off with 3 milliliters of water in a test tube, to which I will add 5 drops of the ester methyl salicylate. Clearly the methyl salicylate is insoluble in the water. Smelling the solution, I find that it has a rather pleasant smell of mint, specifically like the smell of oil of wintergreen. Now I'm going to add 20 drops of sodium hydroxide solution. Remember, this solution is mostly water. It's about 10% by mass sodium hydroxide. The remaining 90% is water. It shouldn't come as a surprise that if we try to mix it, the ester still does not mix with the water-based solution. I'm now going to go ahead and take this mixture and put it in a hot water bath for about a half an hour. The solution has now been saponified, and we notice that there's really only one homogeneous layer at this point. And now we're going to go ahead, and it's lost its smell for the most part. I'm going to go ahead now and put it in cold water to sit. And I'm now going to add hydrochloric acid to the saponified reaction. Although it may be difficult to tell due to the wrestling match here with the stirring rod, the litmus paper did go from blue to red in the spot that it was tested, indicating that enough acid was added. Here we see a solid precipitate being formed. That brings us to the end of Part C and Experiment 17. Thank you.